friends, welcome back for another deep learning project, image segmentation using Unet architecture. So before developing the project, let's discuss on Unet, and after that we will be implementing the Unet. So for that I'm going to Notepad. So Unet is an architecture. Unet is an architecture primarily used for image segmentation and particularly used in biomedical image analysis. Unet has 4 blocks. First one is an encoder. The second one is a bottleneck. Third one is a decoder, and fourth one is a final output layer. So architecture comprises of encoder, bottleneck, decoder, and final output layer. So let's discuss what the encoder comprises of. So encoder is a block which extracts features from the input image using convolution layers. The encoder extracts features from the input image using convolution layers. It comprises of convolution layers with 3x3 kernel size, and that also repeated. So we can write repeated applications of 2 3x3 convolutions along with valid padding. So 2 3x3 convolutions, then we will apply the ReLU activation function after each convolution. So ReLU activation function after each convolution. After that we will use a max pooling layer to pull out the extracted features. Max pooling layer. So the encoder comprises of repeated number of convolution layers with ReLU activation function and max pooling layers, and the kernel size here is 3x3. After the encoder we will have a bottleneck So bottleneck acts as the deepest part of the network, connecting the encoder and decoder. It acts as the deepest part of the network, connecting encoder and decoder. It comprises of two 3x3 convolution layer with ReLU activation, and it won't have any pooling operation. So what it comprises of two 3x3 convolution layers with ReLU activation, and we won't have any pooling layers. The bottleneck's main purpose is to capture the high level abstract features. Purpose of bottleneck is to capture high level abstract features. Then we will have the decoder. So the decoder upsamples the feature maps to restore the original image size. This helps in precisely localizing the segmented regions. I will repeat it again. The decoder upsamples the feature maps to restore the original image size, and this helps in precisely localizing the segmented regions. So what it is doing? The decoder upsampling feature maps to restore the original image size. This helps in precisely localizing the segmented regions. The decoder comprises of transposed convolution layers to increase the spatial resolution. Transposed conv layers to increase spatial resolution. Then in the decoder we will concatenate corresponding feature maps from the encoder using skip connection. Concatenation with corresponding feature maps from the encoder using skip connections. Then at last we will have two 3x3 convolution layers with ReLU activation, after each up convolution. So what we will have two 3 cross 3 convolution layers with ReLU activation after each up convolution, that is transposed convolution layer. And finally we will be having a output layer. So output layer, it comprises of a 1 cross 1 convolution, 1 cross 1 convolution to map the output features to the desired number of segmented classes. So here, if the problem is of case binary, we will be using sigmoid activation function, and if it is multi-class, then we will be using softmax activation function. So this is the architecture of Unet, where it comprises of an encoder, then a bottleneck, and a decoder, and finally a output layer. So let me write the advantages and disadvantages first. Advantages: one is performs well even with fewer training examples, returns high accuracy in object boundary detections, high accuracy in boundary detection, less prone to overfitting, and computationally efficient. Then it can handle multi-class and binary segmentation, handles both multi-class and binary segmentation. These are the some advantages of Unet. Likewise, we have some disadvantages also. The first one is consumes a lot of memory during training. Consumes a lot of memory during training, and this is not ideal for segmenting highly complex structures with overlapping regions. Not ideal for highly complex structures having overlapping regions. And this Unet needs accurate and detailed levels for training. Needs accurate and detailed levels for training, which is also a very big disadvantage of Unet. And it is slow for inference. Slow for inference. These are the disadvantages of Unet architecture. So let's discuss on how to implement this Unet architecture. So I have imported libraries like NumPy, TensorFlow, Keras, Matplotlib and OS. Then to accelerate our training, I am creating the TPU strategy. So to create TPU strategy, first we have to create a resolver and pass that resolver to our TPU strategy method, and you should maintain this code in your notebook to create a TPU strategy, which is mentioned in the official TPU distribute training document. So let's run and build a strategy to use TPU. So yes, the TPU system local is initializing, and you can see we have 8 cores. And from these paths I am getting the images and masks, and don't worry about that. In this dataset you can copy this for images and this for mask. So let's run this. Then I'm generating the dataset from the paths. So using the image dataset from directory method of utils module in Keras, and specifying the path, validation split, labels, whether to shuffle or not, seed to regenerate, subset to return both train and validation data, and resizing the images to this size and having the base size of this. So using the paths, I am creating the train image dataset and validation image dataset. Similarly, I am creating train mask dataset and validation mask dataset. So let's run this. You can see in train images we have 2667 files, and from that 2134 files are reserved for training and remaining 533 files are reserved for validation. Similarly, 2134 masks are reserved for training and 533 masks for validation. After that, I am zipping the train image dataset and train mask dataset to a single dataset using the zip method and saving that in train ds. Similarly, validation image dataset and validation mask datasets are zipped together and saved in the variable val dataset. So let's run this, and to check the batch of images and masks, I am taking one batch from the train dataset and showing the shape of the image batch and mask batch. Let's run this. So you can see in each batch we have 128 examples where the image has height 128 pixels and width 128 pixels, and it is of 3 channels. Similarly, the mask has 128 pixels as height, 128 pixels as width, and also 3 channels. After that, I am converting the image, sorry, not the image, I am converting the mask to grayscale, then normalizing the mask and returning the mask using the method convert to grayscale, and applying that method to the train dataset and also validation dataset. And let's run this. After that, I'm rechecking the image batch and mask batch. So let's run it again. You can see now the number of channels in mask became 1, but before it was 3. So after doing that, I am visualizing the data. For that, I am taking one batch from trained yes, then I am iterating over the 16 images from both images and masks. For that, I have a for loop with range starting at 0 ending at 16 and has a step value 2. Then I am selecting subplot and plotting the image using IamShow method, then removing the excesses of image. Similarly, selecting another subplot for mask and showing the mask using IamShow method, then removing the excess. So let's run this and see the image and their corresponding mask. So here you can see this is the human image and this is the mask. Similarly, this is the human image and this is the mask, and this is the human image, this is the mask, this is the human image, this is the mask. You can see. Now after that, we are going to build Unet model. This is not of exception styled, so let's remove this. Okay, so as I already told that the Unet comprises of encoder, decoder, bottleneck and final output layer. So let's create two methods for a encoder and a decoder. So here you can see we have a method encoder where we are passing input x and number of filters to the method. Then inside it we have a convolution layer with this number of filters, and you see here this is the 3x3 kernel. That's why I mentioned 3. Then we have ReLU activation which will be performed after convolution operation and giving the x input to this layer, then doing the batch normalization. As in the encoder we have studied that repeated application of two 3x3 convolutions. That's why we have two 3x3 convolutions and ReLU activation function in the encoder. Then at last we are returning the output of the encoder. Then in decoder, the method taking three parameters. One is the input X, another is the residual from encoder, and the filters. So it comprises of transposed convolution layers to increase spatial resolution. That's why we have convolution 2D transpose layer with these filters and 2x2 kernel with 2x2 strided and having that input here. After that, height of the upscaled output image if not equal with the height of the residual from the encoder, or the width of the upscaled image not equal with the width of the residual, then we will be resizing it to the image of height of residual and width of residual. Then we are concatenating both X and residual. So as it is mentioned, concatenation with corresponding feature maps from the encoder using skip connection. So this is the skip connection, and here we are concatenating X and residual. After that, we have to pass two 3x3 convolution layers with ReLU activation as mentioned in the decoder. That's why we are again using the encoder which contains a 3x3 convolution layers with ReLU activation function. So let's run this and create this encoder and decoder. Now let's make the Unet model. So Unet model will do first encoding, then we will have bottleneck, then we will have decoding, and finally we will have an output layer. So this is the input layer which takes image of this shape, and first of all we will be using an encoder with 64 filters, then a max pooling layer, then we will be using an encoder with 128 filters, again a max pooling layer, then we will be doing encoding with 256 filters and a max pooling layer, and finally we will be having 512 filters, then a max pooling layer. So this is the part of encoding. Now we will do bottleneck. So in bottleneck we won't have any pooling operation, that's why we just do the encoding with 1024 filters. So I hope you are understanding, and whenever you develop any deep learning project, make sure that what is the output shape and input shape you are providing, so that there won't be any mismatch in shapes. Then in the decoding part, we are passing the first decoder with E5. This is the output of bottleneck to the input to the first decoder. Then to match the shape, and this is the number of filters the output contains 512 channels. So here E4 contains the channels with 512 filters, so that's why I have given E4. Similarly E3, which have 256 filters or 256 channels, that's why I have provided D0, which will be returning 256 filters output. Similarly another encoder with D1 and E2 with 128 filters, and at last D2 and E1 with 64 filters. So this is the part of encoding. Unet is very simple to understand. Then we will have a output layer. This is the final output layer. Here we will do 1 cross 1 convolution operation. That's why the kernel size is 1, which will operate 1 cross 1 kernel. And as we have converted the masks into grayscale, that's why the output is of binary case, which will return either 0 or 1. That's why we have one filter and using sigmoid activation and passing the output of this final decoder to this layer and getting the outputs and saving that in the outputs variable. And at last we are returning the model inputs and outputs. If you don't understand, please relook to the previous part, that is what I have explained in the architecture section. Then come to this part, then you will understand easily the architecture of this Unet. Let's run this. So Unet model is successfully built. So let's compile the model under the strategy scope. So to compile the model, let's call the Unet model and save the model in the model variable, and using the Adam optimizer and binary cross entropy as loss with accuracy as matrix in compiling the model under the strategy.scope. So let's run this. Yes, the model is successfully compiled. So let's train the model with 30 epochs. To train the model, we have fit method. Here I have provided train dataset and validation dataset, a number of epochs, and a callback checkpoints, which will save the weights of the model, and it will monitor the validation accuracy. To create the checkpoints, we have a method model checkpoint. Using that, I have created this checkpoint. At first I have given the path to store the checkpoints. So let's run and train our model. After the final epoch, we have 63% of training accuracy and 59% of validation accuracy. That means very little model is overfitting, so don't worry about that. So our model is trained successfully with 30 epochs. So let's go for model evaluation. To evaluate the model, we have evaluate method, where I have given the validation dataset and pass it the argument return dict equal to true, so that it will return a dictionary containing the matrix. So let's run this. Here you can see the accuracy is 0.59 and the loss is 0.69, which is at this bottom. Then I'm loading the saved checkpoints and loading the best weights from the checkpoints. To load that, I am using the load model method and getting that in the model variable and evaluating loaded model with validation dataset. So it will take some time. Yes, the accuracy is increased. Finally, we are getting the accuracy of 62% and loss of 0.71. So let's do the inference for 5 images, I think. For some images in the validation dataset, I'm not sure how many images it will show. Wait, yes, 5 images only. So for inference, I'm taking the first batch of validation dataset. 15 times I'm iterating a for loop, and inside that I'm getting the original image and its mask, expanding the dimension of the image to get the base size, predicting the mask with that image. Here I'm showing 3 things. One is original image, another is original mask, and the third one is predicted mask. From each of them I am removing the axes. So let's run this. Yes, 5 done. So here you can see this is the original image, this is the original mask, and this is the predicted mask. As our model has only 60% accuracy, so do not expect a more accurate mask prediction. So this is the original image, original mask, and predicted mask. Original image, original mask, and predicted mask. Original image, original mask, predicted mask. Original image, original mask, and predicted mask. After that, I'm saving the model. Model is saved successfully. So to download the model, you can go to the output section here, then here the model, and this is the checkpoints. So you can download by clicking on these 3 dots and click on this button, download, or you can download the checkpoints from this. So thank you for watching the first part. So to create the user interface, I'm using Streamlit, and as we have developed the model with Keras and Tensorflow, that's why I'm importing both Keras and Tensorflow. Then I'm importing the NumPy for numerical calculation and importing the image from PIL to read the image uploaded by the user. First I'm loading the model. So the files here are model.keras. You can see this is the file where model is saved. From that I am loading the model and saving its instance in the model variable, then creating the user interface where I have a first container for title. The title is human image segmenter, which segments human images, and a description about the project. Then a container where user uploads the images So to upload the image in Streamlit, we have a file uploader which allows users to upload the files, and here I am accepting only one file at a time and saving the file in the image variable. Then under the column I have created under the container I have created two columns, one for input image, another for output mask. Under the input image column, if user uploads an image, then it will show the image, else it will show this image which is the default one. Under the output mask column, if image is uploaded or if image is available, then at first I am opening the image. Here I have mentioned the default file path, don't worry about this, I will change it. Then resizing the image, expanding the dimensions of the image to get the batch, and predicting the mask using the image. So let's rename it to mask. And showing the mask with this Streamlit method. After that, having some links for YouTube, LinkedIn and Hugging Face, from where you can get the YouTube video and can connect with me in the LinkedIn and get the code for this project in the Hugging Face. So let's run this. To run this, enter Ctrl Tilt, and if you have garbage you can clear using the clear command and enter. After that, to run the file, type Streamlit, then space and run, then the name of the file, in my case it is app.py, then press enter. It will redirect to this default browser. It is taking some time. Meanwhile, we can search some images like human images. We can use this. Let's minimize this. This is the default image. So here you can see this is the title of the project or model, human image segmenter, and the description is the human image segmenter is a deep learning model based on the Unet architecture designed for precise segmentation of human images, extracting mask with high accuracy. So let's drop this image here. So it is not changing because one thing I already told, that here we have the path, it should be image. This is the output mask of this image. Let's change this image to here, drag and drop. You can see the output of this image mask is this. Let's change this image to here. You can see the mask of this image. Let's change to another image. Let's go with this. So this is the mask of this image. Let's go with this. This is the mask of this image. Let's go with this. Let's go with this. Love you guys. Keep watching, keep enjoying, keep learning. Thank you guys. Thank you very much.